Okay, so this talk is really about software development, and it's about an approach that we put in place in the development of asterism selection for the NGS system for Mavis VLT instrument. It's actually an approach which you could use for any numerical code you want to develop in Python. But it's true that came into our minds for this work, and I thank my contributors Cedric and Guido for providing mostly the AO expertise that I almost completely lack in this work. So we start from the fact that we want to develop numerical code in Python. We know that we are going to use the array programming paradigm, which is what you use basically when you use NumPy, which is a bit of the golden standard for numerical code development in Python. And we want to enforce some good software development practices, like having modular code, separate the problem statement, particularly the mathematical statement of the problem from the algorithms that you will use to resolve it, and of course leveraging the existing libraries. Something that is really often difficult when you develop code, for example, also in NumPy, is then to port your code for GPU execution. And this is one of the main goals of this work as well. So the idea is to put into the loop of development the definition of symbolic functions or expression, if you will. And to do this, we use the SymPy library of Python language, which is a bit of a computer algebra system like you have in Mathematica and other similar softwares or languages. And this has several advantages, which you have listed here. And it's also possible to use this approach because this library provides us with this mechanism called Lambdify that allows you to generate code. In this case, you have NumPy generation of NumPy code out of the box with SymPy. And so you can translate your symbolic equations to numerical functions. So this is a bit of the approach that we have in mind. We start from a SymPy expression, and then we can, in a way, translate these to different backends, or let's say array programming backends. In the specific case, for us, it was NumPy, of course, and QPy. And while for NumPy, we have everything we need from SymPy, for QPy, we needed to extend this Lambdify mechanism. And this is a bit of the software stack that we have in mind. So we developed a library that, leveraging SymPy, NumPy, and QPy, allows you to translate and to execute, of course, your symbolic function in either CPU or GPU. Seeing is the name of this library. Sorry, I have to rush a bit. Basically, I already told you what's the main contribution. And at the same time, another contribution is to develop numerical algorithms in this context. Particularly for us, we needed the numerical integration methods that are, let's say, backend agnostic. So basically, you write your numerical integration method, and then it will work with both backends, which means that you will be able to run it both on CPU or GPU. So here there is a quick overview of what you can do, and also the code that you need to produce these results. Here you have a library of wave propagation methods, and you can play deciding which are the fixed parameters, which are the variables evaluating these integrals, or even just the argument of these integrals, and produce easily plots for the selection of domains that you have done. So this is another example when you where you compare the intensity of the electric field at a certain distance, and you compare computation with the different methods, and then you can zoom in your domain and have a more meaningful comparison. And of course, the output can be also bidimensional, which means that for each of these points in this picture, you have evaluated an integral. So it's a pretty heavy computation, but when you have a GPU as a place where you do this computation, it becomes you have better performances, of course. This was applied, of course, also in the many big equations that we had to manage and evaluate for Mavis. And here you see just one of these examples with pretty not easy to deal with equation. This is one of the many. When you start to assign some fixed values to the parameters, you have a better and manageable integral, and then you can, of course, evaluate these for your needs. So if I'm ready to take questions, if you are interested in this approach, you can follow a bit this suggestion that I give you, and I'm ready to take questions now.
Okay, thank you. So we don't have questions on the Slack, I think. But I have maybe a question related to the execution speed. So yes. According to your experience, the fact that you use Python is not, I would say, an issue regarding the execution speed for the code?
Yeah, okay. There is an appendix in this presentation that I will share that tackles exactly that. Python is notoriously slow if you want to run numerical code. NumPy is notoriously quite fast, you can reach speeds that are comparable to C code if you stick to NumPy. And with QPy and leveraging a GPU, you can have usually, if you set up well your code, a speed up factor up to 10, 20 times respect to NumPy. So this makes it a good tool for also when you also target efficiency.
Okay. Well, thank you very much.